Good morning, and here we are yet again for yet another lovely session of MENG 3310 Fluid Mechanics. So let's see. This is going to be the 8th lecture in the series, and it will be. Today we're going to continue on talking about some material from the Bernoulli Equation. Last time we finished up where we concluded by discussing some introductory aspects of the Bernoulli equation, in particular that it is based around the concept of conservation of energy. In particular, the idea that we're looking at fluids that will not be losing any energy to friction, to pumps, to turbines, or actually gaining energy from pumps and losing energy to turbines, I should say. In other words, the total energy in the fluid is remaining constant as it flows along a streamline. The only difference, the only thing that will change is that we'll exchange energy between the forms of pressure, velocity, and altitude. So let's move on and begin. So today we're going to look at the form of the Bernoulli equation. We're going to look at its form. We're going to look at its components and also look at some simple applications of the Bernoulli system. So you've probably seen the Bernoulli equation before in, say, a physics class, but we're going to reintroduce it now and reemphasize it and have a discussion on it and what it tends to mean. So Bernoulli equation. Let's look at the good old Bernoulli equation. So Bernoulli equation. Bernoulli. Very nice Italian name, I suppose. Sounds Italian.
Yeah.
Okay, I'm hoping I'm not really screwing up my history of science here. Okay, so again, Bernoulli is based all around the one concept of conservation of energy. So, in other words, the idea is that if a fluid goes up a hill, it must work against gravity. If it goes down the hill, it will be working with gravity. So if a fluid goes up a hill, it will tend to slow down as it gains height relative to its starting position, and opposite if it's going down a hill. Now, let us look at something here, though. Let me draw out a system that is a little more complex than just the simple block going down the ramp that we looked at last time. So I'm going to draw a pipe, and this is not actually my poor art skills. I'm actually deliberately drawing it with one end much narrower than the other end. So that's not just my poor art skills. This is actually meant to be narrowing as it goes up the ramp, or as it goes up the pipe. So we have a pipe that is simultaneous, sort of generic pipe, that is simultaneously narrowing and raising in elevation. So let us look at the 2 points 1 and point 2. So I'll show a cross-section here and a cross-section here. Here we're going to have a cross-sectional area of a cross-sectional area A1, a pressure P1, and a velocity V1. Then up here, we're going to have a velocity of V2, an area of A2, and a pressure of P2. Then let me show that we have the elevations, let's say Y1 and Y2. We have the elevation at each of these points. This one is Y2, and this one is Y1, and the difference is going to be h. The difference between the elevations is h. Now, we can actually conclude something interesting, even without looking at any other energy, even without looking at any energy considerations, and that is that because the area here is much larger than the area here, I already know that velocity 1 must be much lower than the velocity 2. So if I look at a system of and we'll get more into this when we talk about continuity later in the semester. But if I look at a system like this, just a simple narrowing pipe, ignoring the elevation change, even without considering any kind of energy considerations, if I have a pipe that is becoming narrower, if this thing is going to not have any voids in it, any bubbles, anything like that, as long as it is in what we will later refer to as a steady state, there must be just as much matter coming into one end of this pipe as the other. So, in other words, if we have like an m dot 1 and an m dot 2, m dot representing matter, or we could also say v dot, say like the flow rate of volume, a volumetric flow rate. Both of these have to be the same. V dot 1 must equal V dot 2, or M dot 1 must equal M dot 2. This is based on the continuity of flow. So this is going to be something that we'll use many times as we apply the Bernoulli equation. There must be as much matter, this is regardless of the amount of energy involved, there must be as much matter coming into this thing as coming out of this. The only way that this would not be true is if maybe there's some air bubbles piling up, or maybe if the now the volume is a little bit trickier. The volume is not necessarily always conserved, especially if your fluid is, say, compressible. If your fluid is compressible, it could simply have a greater density here than over here, and you wouldn't necessarily have the same volume coming in as going out. But the one that will always be conserved is mass. You will always have the same amount of mass coming into a system as leaving it. The only exceptions would be if there is some sort of air pockets being formed, the system is initially filling, or if there's some really weird nuclear reaction going on that is destroying mass, and that would be releasing so much energy that the whole thing would be going up in a nuclear fireball. So typically we don't worry about such things. Anyway, in terms of our normal systems, anyway. So yes, if half the mass of the fluid is just disappearing, well, E equals mc squared, that's going to be a lot of energy released. So typically we don't deal with such crazy systems. And typically nobody deals with such systems, and the only time that we do have nuclear reactions in nuclear reactors, they do transform a small amount of matter to energy, but even then you're talking about 0.01% of the mass energy spread out over years or something like that. But anyway, that's neither here nor there. So again, if we're looking at something like water, oil, any kind of things like that, any type of liquids, we're typically dealing with non-compressible fluids. We're going to be talking a lot about those. We're going to be applying those a lot in this class. So if we use a non-compressible fluid, in the sense that its volume will not substantially change when under different forms of pressure, different levels of pressure, then the volume coming in will equal the volume coming out. And so we can actually use the relationship, and we'll have a relationship that we can use at points through the day today. If volume dot 1 equals volume dot 2, or more commonly referred to Q1 equals Q2, well, Q is your volumetric flow rate, or V1A times A1 equals V2 times A2, where the V1 here and V2 here are velocities, not volumes therein. And actually, if I was going to be consistent with what I've used previously in the semester, if I'm going to use a V for volume, I might just use a barred V here. But anyway, that's not really this kind of conservation of volume isn't necessarily inherent to Bernoulli. The Bernoulli equation will apply regardless of if the fluid is compressible or not. But the conservation of mass will always apply, and the conservation of volume will be a very useful tool that we can use as we also apply Bernoulli's equation. So again, I just wanted to sort of justify why I'm saying that there is up here there will be a small cross-sectional area and a large velocity. Down here there will be a large cross-sectional area and a small velocity. And again, there will be the same amount of matter coming into the tube at this side as is leaving at this side. Okay, now let's move on here and look at how, say, pressure would work. So let's say, what if the fluid were static? What if it weren't moving at all? If the fluid were static, how would things look? How would pressure behave? Behave. I lost my B here. Well, if we remember from earlier material, if it were static, if the hydrostatic condition were in control, we could simply use Pascal's law. We could also use Pascal's wager, but that would lead us to a very different conclusion. Philosophy joke. Equals, so P2 minus P1 equals rho times G times Y2 minus Y1. Or simply rho GH here. Now, something interesting here. Pascal's law, this reminds me of something. Pascal's law, rho GH. This reminds me, what I'm going to try to do is, I'm going to try to build Bernoulli's equation kind of in a sort of a, maybe not the most rigorous mathematical proof, but kind of an intuitive way. I want you to try to get a very intuitive understanding of how Bernoulli's equation really works. Pascal's law, what this reminds me of, if I remember from my high school physics class, this really reminds me of gravitational potential energy. So, gravitational potential energy, if you recall from high school physics, well, potential energy is mgh. So, what if I constructed it per unit? Like what if I wanted a gravitational potential energy per unit? Like a unit gravitational potential energy. Potential energy. In other words, what if I divided this by volume? So what if I said here, well, if I did mgh over volume, well, isn't density just mass over volume? Density is just mass over volume. So effectively, this equals rho GH. Or in other words, rho GH is equal to gravitational PE per volume. So basically, therefore, and since this is P2 minus P1, since I already know that rho GH is equal to P2 minus P1, I can actually conclude something about those units of pressure. Therefore, P2 minus P1, or just units of pressure in general, has units of energy over volume. This completely transforms how we think about pressure. This may seem small, but this is actually a transformational way of looking at pressure. You first learned that pressure equals force over area, and that is the simplest definition of pressure. But another way to think of pressure is it really represents the energy per, it's a way of looking at the energy per unit volume, the internal energy per unit volume, well, ignoring thermal energy and things like that. But it's a way of sort of measuring energy per volume. Pressure literally has the units of energy per volume. So that's a very key concept to be aware of. It's a way of transforming our understanding. If you remember back from your study of electricity and in your physics courses and electrical circuits courses, the way I kind of think of pressure, if I say, something like volumetric flow rate is equivalent to electric current, well then pressure would be equivalent to voltage. Pressure is kind of equivalent to voltage in an electric circuit, in a fluid. Sorry, if the analog of voltage in a circuit, but in a circuit of fluid is pressure. Pressure really represents internal energy. Okay, so we've looked at how pressure works. Now let's try to set this system in motion. Let's get things moving. So previously we were working with a sort of application of Pascal's law where everything is sitting still. Now let's set the system in motion. Let us set the system in motion. And I would also like to construct everything as a unit energy. And so let's take a look at how we might do this. Well, KE per volume. Well, I know that KE is 1/2 mv squared divided by volume. And hey, mass over volume. Again, this is just now density. So we could also say Ke per volume is 1/2 rho v squared. So now we see that we can also express motion as a unit quantity. So I'm going to create an equation that combines all of these in unit terms. By unit terms, I mean per unit of, say, volume, or, we could even also construct it per unit of mass or something like that. We would end up with you can't actually express Pascal, you can't actually express Bernoulli's equation in, say, in mass terms, in terms of mass and things like that, or in terms of unit mass, but you just end up with a slightly different derivation. So, again, let me summarize. We have 3 players on the board. We have Ke over volume. We have K. Huh?
Oh, sorry.
Sorry. We have Ke over volume. Pe over volume. And pressure. And all 3 of these in systems that do not lose energy, all 3 are equal partners. All 3 are equal partners. So Bernoulli's equation will represent the change or the transformation of one of these into another. We can, if we want to make the fluid go faster, we either have to trade some potential energy, or we have to lose some energy from the pressure. If I want to pressurize a fluid, if I'm not inputting any energy into it in the form of, say, a pump, well, then I have to pay for that somehow. And the way I pay for that is either via making it go down a hill to decrease my potential energy, or I make it lose velocity. One or the other. There is no such thing as a free lunch in terms of energy. And heck, when we see fluid losses later in the semester, we'll see that we can't even break even. There is no such thing as a free lunch. This is just like what you learned in conservation in physics class, the conservation of energy. This is all about conservation of energy. So I can get more Ke, but I'm going to have to pay for it in terms of Pe or pressure. I can make water go up a hill by, in other words, increase the potential energy, but in turn, I'm either going to have to lose kinetic energy, I'm going to have to make the fluid go slower, or I'm going to have to lose pressure. There is no such thing as a free lunch. And so I can trade one of these for another, but I can't increase the total amount of energy I have unless I directly apply work to the fluid, say via a turbine or something like that. Or when you get to your, say, your heat transfer class later in your academic careers, you will see that another way to add energy to the system is by adding heat. Now, this is not a thermodynamics class, so we're not going to discuss adding heat energy to the system, but that is sort of but we will discuss pumps, turbines, things like that. But the next logical step, if you're looking at it from a mechanical engineering point of view, is to start looking at adding heat to the system, and that's where you have a thermodynamics course. Or actually, I believe a heat transfer course in particular. So again, we have all 3 of these. The sum of them should be constant, and this is the fundamental idea behind Bernoulli's law. So 1/2, actually let me do, 1/2 rho v squared. That doesn't look quite like rho like I'd like. 1/2 rho v squared plus rho gh plus p equals constant along a streamline. And in case you're not aware or remember, a streamline in a fluid is the line that a particular particle of a fluid would, or the particular particle, or particular molecule, or particular atom of a fluid will take as it flows through a pipe. So you can trace streamlines by simply releasing a stream of particles into a fluid flow and watching what kind of shape they would make within a pipe. But anyway, that's more of a definitional thing. So usually we're not talking about individual streamlines in a pipe. Usually we're talking about the average velocity or the average pressure along a surface. So we have this. Now, let's say I divide. So I want to modify this, though. This is not the usual form we use. Usually we use something slightly different, and we do this by divide by rho, or actually divide by gamma, or in other words, divide by rho times g, or gamma. So if I do this, I can get a slightly different expression of Bernoulli's equation. and that is v squared over 2g plus z plus p over gamma is equal to constant along a streamline. Streamline. And this is the form that we'll be using through most of the semester. And this fundamentally is our main form of the Bernoulli equation. And this will be one of our single most important equations for this entire course. Again, so when I move a fluid element in a tube, I trade speed for height and pressure, etc., etc. Okay. So next, I would like to look at I'd like to remind us of the assumptions behind this, just so we are very clear about what the assumptions are and when we can apply it. Bernoulli can be useful, but it is not universally useful. There are certain times it's appropriate, and there are certain times it is not. And you, as practicing engineers, need to be aware of the limitations and assumptions behind your equations. Otherwise, you'll find yourselves designing machines improperly or reaching improper conclusions. So the assumptions are, first, in viscid fluid. What do I mean by this? In viscid flow, we discussed viscosity before, but viscosity, again, when I say a viscous fluid, I think of something like molasses or tar or something like that, something that's going to resist flow. And in other words, usually it's going to flow very slowly. It's going to resist flow. It's going to basically generate a lot of internal friction as it flows, that kind of thing. So what we're really assuming is we're assuming a fluid with zero friction. We're not losing any energy to friction as a fluid flows through the pipe. So that's not a perfect assumption. In reality, that's impossible. You will never have there is one case where you can actually have a truly inviscid flow, like a literally zero flow, but it's not anything that you'll be designing with. The one exception I can think of is superfluids, such as liquid helium or something like that. Those actually do, just like superconductors have zero resistance to electrical current. There actually is at very cold temperatures, cold enough to a fraction of a degree Kelvin, that kind of thing, where you can get liquid helium. It actually can flow with zero viscosity. So if you get a current of liquid helium flowing, it can actually theoretically just keep flowing forever as long as you keep it flowing, as long as you keep it at that super cool temperature below its transition state. So there are a few very niche cases where you could actually get perfectly in viscid flow, but in basically any kind of material or any kind of fluid you'll be dealing with, unless you're designing MRIs or something, there is typically no case that you'll actually be dealing with actual superfluids, truly in viscid flow. But even though I say that even though I admit that this is completely impossible, this isn't actually that bad. For most of the fluids that we deal with, where we use Bernoulli's equation, this assumption is not perfectly fine, but it's good enough. It's good enough. Everything in engineering, everything in physics, everything is built on a certain set of assumptions. We assume certain things are going to be minor. We assume certain things can be safely ignored. We assume certain things are not going to contribute meaningfully to the system. So, for example, a trivial example of where I would ignore something is, if I'm designing a structure, if I'm designing a bridge, I need to consider all the forces acting upon that bridge. Now, intellectually, I know that one force, so the biggest forces that I'm going to consider are the weight the bridge is going to have to carry, the weight of the members itself, the weight of the wind, any rain that falls on it, snow load, those kinds of things, and the gravity of the earth, all that kind of thing, all those kinds of things. But I know intellectually that gravity acts from every object in the universe to every other object in the universe. I know intellectually that the gravity of the moon is actually acting on that bridge and generating very, 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 very small, tiny loads that continuously change in direction as the moon orbits around the Earth. Now, but I know also that those are so small that I don't really need to consider them. I could never actually consider every single force that acts on an object if I were trying to design it. I can't design something perfectly, even because even if I'm only looking at gravity, well, there's an infinite number of planets and stars and galaxies and things out there. If I tried to model the gravity of all of them, well, it would be impossible. So at some point, we always have to put a limit on our analysis and say, you know what, I don't need to worry about the gravity of anything except the Earth. It's not important. The only thing that matters is the gravity of the Earth. Everything else is just tiny, tiny nanograms of nothing. And so now the viscous flow of water is not as dismissible as the gravity of the moon, but it still is. At least for certain conditions, at least for certain systems, it doesn't become important. Now, if you're designing something where you're dealing with many miles of pipe or or hundreds of feet of pipe and things like that, well, in those cases, you actually have to start dealing with the viscous losses, and we'll learn how to calculate those later in the semester. But for certain applications, we can't ignore them, and since we're starting from the beginning of fluid mechanics, we're just at the baby steps right now, we'll assume that no fluid energy is lost to viscous forces. Steady flow. This is another assumption. Steady flow essentially means nothing is changing, in the sense that what I'm talking about is a steady state. So what I mean by a steady flow is, say I have a pipe, there is fluid flowing into it and fluid flowing out of it. Well, if you want to think of non-steady flow, think about what happens when you first turn on a garden hose. Initially, it's full of air, and as the water flows from the tap into the hose, it has to force all that air out. And so that you hear that kind of gurgling, you hear that sort of, you hear all those bubbles being formed, you hear a very turbulent condition. Water is mixing with air, and the water is quite rapidly in some cases, forcing the water out of the hose. And that's a very sort of turbulent, violent kind of process, and we can't model that with something as simple as a simple equation like Bernoulli. You can't actually model that with more detailed, you can't make exact predictions, so you can't actually model it using more finite element type type models, but beyond the scope of this course. But in terms of actual Bernoulli, that is not a steady state. The thing is continually changing. There is the air is being forced out, water is taking the place of air. That is not steady state. What steady state is for the garden hose is give it 30 seconds, and after all of the air has been forced out of the system, then things calm down and you have a nice even flow coming out of the garden hose. That's what I mean by steady state. We have reached a state of equilibrium. There is just as much water coming into the hose as leaving the hose, and now things have calmed down and they are sort of normal. There may still be changes of energy going on within the system in the sense of trading pressure for velocity, pressure for height, that kind of thing. But we have reached a steady state. So steady flow is an assumption. We're also going to assume incompressible flow. At least when we're dividing by velocity and using gamma and things like that. Bernoulli actually does assume incompressible flow. I guess I think I might have said earlier that we could use this for compressible flow, but actually I don't believe that would be appropriate for the way we've derived it. You could modify it for a compressible flow, but not for the way we're using it. So again, incompressible flow. Now, in reality, nothing is incompressible. If you had a perfectly incompressible fluid or a perfectly incompressible object, you could do all sorts of really weird things with that. You could send a signal faster than light if you wanted to. You could just tap on one side, and the vibration would instantly be transmitted to the other side. You could violate causality with that, send messages back in time. You could do all sorts of really screwy things if you had a truly incompressible object or fluid. But we don't have to worry about that because in reality, no object is perfectly static or perfectly rigid or perfectly incompressible. Everything is compressible to a certain degree, but, so don't worry about some of those weird things I just said. They're technically true if you look into it, but don't worry about it. Just don't worry about it. It's okay. Don't think too hard about it. Anyway, let's just say from a physics point of view, if you truly had an incompressible object or fluid, you could do all sorts of really screwy things with it. It transmit infinite amounts of energy if you had an infinitely rigid material. True, as well. Two, I should say. But anyway, nothing is incompressible. However, this is one of those things, again, where we can say close enough. When I apply a large force of a large pressure, a large compression force to water, even if I look at the depths of the ocean, miles and miles of water above the point at the Challenger Deep or something like that, you're talking about a tiny, tiny fraction of 1% in the increase in the density of water compared to the surface of the sea. It does change very, 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 very slightly, but it's so small that we can usually neglect it. And then also we can assume flow along a streamline. This just means we're looking at, as long as we're looking at the average energy with the average flow within a pipe, that's going to be perfectly fine. The average flow along a streamline. Okay. So let us look at applying. So this is Bernoulli's equation. We've learned how to define it. We've learned how to derive it. We have learned the assumptions behind it. We've learned what goes into it. Now let's look at a few applications of it. So applying the Bernoulli equation.
What was the last assumption?
Sorry, the last assumption was flow along a streamline. So applying the Bernoulli equation. Okay, so remember how I mentioned previously, now back here, I said that this is constant. Right here. I said that all this stuff is constant along a streamline. Now, we could use that. There is a form we could say, we could use it as it's written here. We could just say, oh, at some point we'll calculate a number and we'll just make sure that number is always the same and do a lot of math as we go along. But often it makes more sense to compare two different points directly. We usually don't actually calculate the total energy in a system. Usually we do some sort of a point 1, point 2 type analysis that you may remember from physics or from other courses. It's a very common thing to look at in physics, in chemistry, in engineering courses. This kind of general kind of state 1, state 2 comparison. And the nice thing about this is that you don't have to calculate the total energy. And the other nice thing about it is often you sometimes have things that one of these terms will be the same in each case. So for example, if the height doesn't change from point 1 to point 2, you can just cancel out the z term and it becomes a lot easier. But anyway, let me just show you what I mean. So P over pressure, this is again pressure over gamma plus velocity squared over 2g plus z. All of these for 1, so like pressure 1, velocity 1, z1, gamma and g would not have any kind of subscript on them because they are going to be constant throughout the system. Then P over gamma plus v squared over 2g plus z is going to be equal here. So the sum of all of these for state 1 is going to equal the sum of all these for state 2. Now, again, so the advantage of this, the advantage of doing it this way is, or at least one place where it would be useful is, one use of this method eliminating constant quantities. Eliminating constant quantities. In other words, let's say I had a fluid here that went through a pipe change in diameter. So we have a transition pipe here, and the pipe will change in diameter. And the streamline that we're going to be looking at is right down the center of the pipe. And I'm going to have I'm going to have an A1 and a V1. Let's say P1, A1, so pressure 1, area 1, and then a velocity 1, V1. And then over here, I will have a P2, A2, and a velocity 2, V2, lowercase v velocity 2. Now, again, this here, there is no change in height. So since delta H equals 0, Z1 is equal to Z2. that means we can cancel out the middle term. We can cancel out the z term. Z terms cancel out. Therefore, the Bernoulli equation collapses to, we simply have P1 over gamma plus V1 squared over 2G equals P2 over gamma plus V2 squared over 2G. Here. And so again, this is the advantage of using this kind of form here where you compare two different states. Again, I just want to reiterate the importance of this, or the usefulness of this. And again, the usefulness of this is where you have a one of these terms is the same, you can simply cancel out a term that is going to be identical. And so this allows you to, otherwise if you did it using the equals a constant method, at one point you'd have to run through all of the calculations, calculate a constant, a literal number, a constant for the system, and then you'd have to go and do a lot more math again, subtraction, etc. And you wouldn't necessarily be able to as quickly reach conclusions. In fact, just looking at this, even without doing any math, I can conclude that V2 is greater than V1. I know this from, V1 is greater than V2. V1 is greater than V2. I know this from simple continuity considerations, as we saw earlier. If the pipe is going to increase in diameter, it must lower in velocity as long as conservation of volume will apply, and conservation of mass. And even now looking at this, so I got this from simple conservation of volume flow rate, or conservation of Q. And from this, looking at Bernoulli, if this term is greater than this term, the only way this can be true is if P1 is less than P2. So since there's no change in height, let's look at this from an energy point of view. There is no change in height here. This pipe is level the entire way. The center line of the pipe is a perfectly flat line. Maybe it doesn't look that way because of my poor art skills. But in general, at least as I meant to draw it, it is a perfectly horizontal line. And so we cannot get energy or lose energy from, we cannot get or exchange energy with height. So therefore, here, as the fluid flows along here, it is decreasing in velocity. In other words, it's losing kinetic energy. It's losing kinetic energy. And so therefore, what must happen is, if it's losing energy as it goes from here to here, the only way it can do that, and that energy has to go somewhere. It's losing energy as it's going from here to here in terms of kinetic energy. It's losing kinetic energy. The energy does not just vanish. It has to go somewhere. And where it goes in this case is it goes into pressure energy. It's going into pressure. Pressure is energy. I want you to just really start thinking of pressure as energy per unit volume. Pressure is energy. Okay, so let's look at another example. This one, let's see, I'm going to go through a short derivation. I'm going to look at a siphon. And a siphon is a tool that can be used to extract water from a tank or something. It's what gas thieves use to steal gasoline from automobiles, but let's not worry about that. This was a big problem back in, I guess was it the time of really expensive gas prices when gas was about $4, $4 a gallon, things like that. You saw people would come out to their big trucks in the parking lot and find, I don't know about this school, but at least there was a couple cases around Houston. People would come to especially their big old trucks in the parking lot and find that their tanks were mysteriously drained. And it got so bad that manufacturers actually have started putting anti-siphoning devices built right into their gas tanks. But anyway, but it can also be used for non-evil purposes, such as draining a pool is very common. You can use it for that. You can use a siphon for emptying a fish tank if you don't want to, especially if you have that can actually be a big problem. If you have a really big fish tank, for example, if you have a really huge fish tank, if you want to clean that out, just emptying it out can be a real pain in the butt. You have to 1 gallon at a time pull water out of it, and it can be a real pain. So a nice thing to use is a siphon. And it works via really continuity and energy considerations. So say I have a fluid here. Let's just use water, row water. Let's say row water here. Row water. And I'm going to say that this is going to be P2 up here. We're going to have a point 2 up here. P2, the pressure up at point 2 is just 1 atmosphere in terms of absolute pressure. And I have a siphon. And the whole idea of a siphon is that you're going to first raise the water up a little bit, but ultimately you're going to drop it down to a much lower elevation. You're ultimately going to drop it down to a much lower elevation. And you have V1 here. And this whole thing is full of water. And in case you're not familiar, this can be often this is done with a simple garden hose or something like this. V1 and P1, well, it's also 1 atmospheric pressure, 1 atmospheric pressure. The pressure may change as it goes through the pipe, but we're not concerned about that. We're looking more at the beginning and the end, and so I'm going to look at the atmospheric pressure. I'm only going to look at the pressure at each point is just going to be atmospheric pressure. Let's say this is D here, distance D. And then I'm going to call this distance H. H, and this one being Y1, and this one being Y2, and Y is going to be measured from the bottom at 0, and this way positive. Now, the whole idea of this is that you, if you're not familiar, is you just have to get the flow going. That's the only time you actually have to apply work or energy to the system. So you have to apply enough energy. If you're using water, I suppose you could just suck on the tube. If you are using gasoline, I don't suggest you do that. Or you could, if you're dealing with a larger system, like if you're doing like an industrial system, you would use a pump to get the siphon going. But it's not uncommon for people just, suck on the tube essentially with their own, lungs. But you got to be careful with that. I don't recommend doing that with gasoline, etc. But the whole idea is you apply suction, essentially a negative pressure, via essentially pulling on the tube either via your own lungs or more commonly industrial settings, a pump, and you apply essentially a lower pressure here than here, and this causes fluid to flow up the tube and then down. Now, so that's the only time you actually have to apply suction to get this thing going. And after that, well, the water in the column is accelerating as it comes down. And so there is an overall increase in velocity energy, in kinetic energy of the fluid. And after that, everything just keeps going. So water tends to flow down a hill. We know this. Water likes to seek lower places. And so water likes to seek lower places. And all you're really doing with the siphon is giving it a means to overcome the height boundary of its container. And once you get the initial thing going, then the pressure of the fluid allows you just to keep going by itself. It's almost, if you ever worked with a siphon, even they almost seem like magic at some point where you get this thing going and it just sort of keeps going all by itself. It's kind of cool. It is kind of cool to see it's just simple physics and simple fluid mechanics, but it is kind of a really impressive application of a thing where you get a fluid going and it almost by magic, it just sort of makes itself flow out of the container. It's kind of cool if you've ever played with a siphon before. But anyway, that's...
Is a siphon like an actual tool? Can you use any type of pipe?
You can use any, so the question was, is a siphon an actual specific tool? Now, in certain applications, they might actually make dedicated devices intended to be used as siphons, especially if you're going to attach a mechanical pump, you'd probably need something special. You might need something special to go for that. But, you can use a fish tank and a garden hose. You can use just any tube that's equivalent, that's appropriate. So yeah, you can literally empty a fish tank with a garden hose, a long garden hose. So all that's important is that say your fish tank is elevated on a table or something, you would want your you would not want the end of the garden hose to be on your living room floor, or else the entire tank will end up on your living room floor. You would want to run the hose out your front door or something and into the lawn or into a storm drain or something like that, or just the kitchen drain even. All that will matter is that you just have to make sure the end of this tube is lower than the point where you are pulling water from. And Yes, it's a process. You're basically giving a path for an exchange of gravitational potential energy to take place. And so let us look now at this from an energy point of view. So again, Bernoulli's equation is P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. Now, we're going to start canceling things out. First of all, I'm going to get rid of the pressures. They're the same on both sides. They're atmospheric pressure, so those just go away. Then I'm going to say V2 goes away because V2 is approximately 0. Now, right at the edge of the boundary, right at the cross section of the pipe or the tube, the velocity won't be 0. But I'm comparing this point to this point, right at the surface. Basically, when you immerse a fluid or a pipe in a fluid, or you're looking at a fluid entrance, there is sort of a velocity field where a pipe meets a chamber, or a pipe meets a tank, I should say. So if you look at this, if you have a pipe going into a tank, well, here you have a velocity, but then you sort of get a series of velocity arrows that get smaller as you go further away. So close here you have the max velocity, here you have very small velocities and larger velocities, and over here you essentially have 0 velocity. That's how fluids actually work as they are that's how fluids actually flow from tanks into pipes. You start with 0 velocity around this boundary, and then there's a slow transition region as you go towards the pipe. So if I look at this, then if we look at what cancels out, V1 squared will equal to 2G times Z2 minus Z1, or V1 is equal to the square root of 2GH. V1 is equal to the square root from 2GH, or the square root of 2GH. Now this should look familiar. This should look familiar. If you remember from physics class, this is identical to the equation for simple freefall. If I drop a pebble from a height and if I ignore air resistance, this is the equation for its velocity. This is the same exact thing. So this does connect back to basic physics. And finally, I just want to mention one restriction on this. There will be one restriction on this. The restriction on this will be that D must be less than approximately 10 meters. Because ultimately the only way you can pull fluid out of this is to get the initial siphon going. You need to, what initially pushes the water up, it's not necessarily being pulled up, it's that there's vacuum being formed here, and atmospheric pressure is going to force the fluid up to the top of the tube, and then gravity takes it back down. But as we've seen before, air pressure can only push so far. It can only cause fluid to rise so high against a vacuum. And if you are greater than 10 meters, you're going to start pulling vacuum. Because barometric pressure, or because atmospheric pressure can only raise a column of water up to about 10 meters. Raise a column of water.
That's for every case?
Yes, that's for every case. Now what you could do, if you'll forgive me a bit for going over time, is if you had a really crazy case of, let's say you wanted to get water over a mountain range. So there's a mountain, big old mountain, but let's say there was a coastal plain here and an elevated plain here. Theoretically, there could be a siphon here. Now, you could drill a tunnel through the mountains and take your water that way. Let's say you want to there's a mountain lake here, and let's say there's a mountain lake here, and there's a city reservoir down here that you want to bring the water from here way up in the mountains to down here to provide water for the city. Now, you can't use you can't just rely on air pressure to get that water over the mountain initially. Now, I don't whether this would actually work or not would depend on the specifics of the So basically, you want a pipe going over the mountain, right? This is not to scale. You would want a pipe going over the mountain. Now, but you can't just pull air on this end and have air pressure push the water up the column a mountain high. This thing might be a mile or two high. If this is 10,000 feet, there is no way you're going to be able to push a column of water that high, relying on atmospheric pressure. But what you might do is you might have a pumping station down here. You could have a pumping station that pressurizes the system initially and forces the water up the hill. And you might actually, I don't know if you actually could do this. This would depend on the actual amount of fluid losses along the walls of the pipe. But if the losses were minimal, you could use this pumping station not to continuously pump the water, but just to get the siphon going. And then you could just turn off your pumps and just let gravity do all the hard work. So you'd only have to expend a lot of energy once in order to get the siphon going, and then you can just let the water flow through the pipe nigh on forever. And this one here, this reservoir here, will continually to drain in the lower reservoir just based off of siphon action alone. So you would have to use pumps, but only just to get the initial thing going. And you have to rely on pumps at the bottom to push water up the hill rather than relying on a pump down here to initially pull water up the hill. All right, that'll do it for today. I hope you enjoyed the lesson. If you have any questions, feel free to see me during the office hours. And as always, thank you.